have studied in the advanced level, right? Let's see from that point onward how you can get more and more knowledge so that you can think about complexometric titration. Okay, right. So let's see. Go to the next go to the slide number 1 here, the slide. So you can see the complexometric titration. Likewise, in any other titration methods so far we have studied, acid-base titration and precipitation titration. The name of the titration itself tells you what sort of reactions are taking place in the reaction, right? In the precipitation reaction, the precipitation reactions are taking place. Likewise, here in acid-base neutralization titration, the reaction happening, that's a neutralization reaction. Here, the titration, where the complexes are formed. That means during the titration, so what is happening there? The reaction is happening, and we get a complex, right? So these methods are called complexometric titrations or complex formation titrations, right? You can call them either complexometric titration or complex formation titration. So the complex formation for the titration, now you know there should be a reagent. Here the reagent is the complex formation reagent, right? You have in the burette complex formation reagent. So this sort of titration, the complex formation, complexometric titrations are very, very widely used for the determination of metal ion concentrations in samples, right? Anyway, what you have to do, if it is a solid sample, you have to extract the metal into a suitable solution and then do the titration, right, with the complex formation reagents. So these reagents, what are these reagents? These reagents are in fact organic compounds. These reagents are in fact organic compounds that contain several electron donor groups. Now you have to understand what we mean by the electron donor groups. So the complex formation titrating reagent or the complex formation reagents are organic compounds. Particularly, they contain several, right? You just look at that. It says several, right? Contain several electron donor groups, right? What are the electron donor groups? What you say the complex formation reagent contain, this is a part of the complex formation reagent, and this, you know, the nitrogen, it's unpaired electrons, right? These are also we call lone pair electrons, right? We call them lone pair electrons. Lone pair electrons, right? They are lonely there. So anyway, they are available to make some sort of bonds with the metal ions, right? So the for the complex formation reagent, there should be in the molecule more than 1 or 2 or 3 or 4, like that, the electron donor groups, right? And what happened, as I mentioned earlier, they form multiple covalent bonds. They form multiple covalent bonds. If you think about something like this, look at here. What is this? Ethylene diamine, right? This is ethylene diamine, right? And here on this nitrogen also that's a lone pair electrons, right? So with the metal ion, if you have the metal ion here, just put M, can make a bond with this one and this one, like this, right? So like that. So the both the electrons are from the reagent, not from the metal ion, right? So metal ion can accommodate electrons from the donor group, and finally you get a bond formation between that electron donor group and the metal ion, right? The metal ion accommodate electrons there, and then both the electrons of the bonds are covalent bonds. The bonds are covalent bonds. So I have mentioned here the bonds are covalent bonds. That means 2 electrons are shared. But the important thing, both the electrons come from the reagent, complex formation reagent, right? So right. Then the complex formation reactions, right? The Morse metal ion, it's very important that the Morse metal ion react with electron donors to form coordination compound. The compound, the metal ion compound, thus we get in reaction with metal ion, your reagent, the complex formation reagent, react with the metal ion, right? What you get is they are the complexes. They are the complexes, or they are also called coordination compounds. Coordination compounds. And particularly these electron donor groups, you just get to know about this one. The electron donor species are called ligands. Very, very important. Okay, what is a ligand? Then you have to define a ligand, right? So this particular one, this particular thing here, ethylene diamine is a ligand, right? It is a ligand. That means if you want to write the definition for a ligand, you can say ligands. A ligand is, you can see the ligand is, and it can be an ion or a neutral molecule, right? That forms a covalent bond with the cation or neutral metal ion. How it is formed? By donating a pair of electrons, right? I just use L, that's a ligand, and you have the neutral metal atom or charged one, and here you have on the ligand unshared electron, lone pair electrons, and this is how you indicate the bond formation. Right, it is by donating both electrons from the ligand to metal. Now the bond is formed. This bond is called coordination bond. Right, it is called coordination bond. This is called coordination bond, and also it is called dative bond. Okay, DATIVE. Okay, this particular bond here, it is called either a coordination bond or a dative bond, right? Now, example for a ligand, water molecule here. Water molecule, you can see the water molecule here. It has 2 lone pair electrons there on oxygen, right? So you can expect water molecule to make a bond with metal ion by sharing its lone pair, by donating its lone pair electron. And even ammonia, right? The ammonia, there's 1 lone pair electron. So the thing. These are neutral ligands. These are neutral ligands. Similarly, you can think of ionic ligands, anionic type, chlorine, chloride ion, and it has how many? Like 3, something like that, right? So you can think they also can make coordination bonds with the metal ion. So right. So we then move to the next slide. The next slide. Then it's the coordination number. The coordination number, by definition, it is the number of covalent bonds that the cation tends to form with electron donors, right? So simply, what is the number of coordination bonds a metal ion can form or make with ligands, right? So they make with ligands. Then the like if we can take a very typical value of the coordination number, can be 2, can be 4, can be 6, right? The coordination number of a metal ion. Actually, here the coordination number always referring to a cation. So the coordination number of a cation, it can be the 2, 4, or 6. One of these, so 2 can be the 2, right? So if we take copper 2 plus, cupric has the coordination number of 4, right? That means your copper 2 here, right? It can accommodate 4 ligands here, right? So it can make 4 bonds with ligands. For example, ammonia, another ammonia molecule here, NH2, another ammonia molecule here, and another ammonia molecule here, right? 4 coordination bond, 1, 2, 3, 4 coordination bond, right? The copper, the coordination number, copper 2, the coordination number is very common one. It is 4, right? So with the same metal ion, when it combined with ammonia, right? What you get, the ammonia doesn't carry any charge, right? Here, sorry, NH3, right? It is NH3. Ammonia doesn't carry any charge. It is a neutral one. So what is the total complex now? The total complex here, it is positively charged 2+. Right? Similarly, with water it form cationic complex like this one. Right? With glycine, you know, it's an amino acid. We studied about amino acid very briefly. Their dissociation, right? Look at here now. The copper has copper 2. You know it has coordination number 4, but here 2 glycine molecules here. Each glycine molecule can make 2 bonds. Each glycine molecule can make here the oxygen, and from other side is ammonia, nitrogen, like this. The other part of the molecule is somewhere here. Other part of the molecule somewhere here. Right? 2 glycine molecules, one from this side and the other from this side. Again, 4 coordination. One, this one, this one, this one, and this one. Right? So the look at here that particular thing here is the glycine. You get the carboxylic part. It is the -1 deprotonated. So the copper 2+, the entire complex now it is neutral, right? So this is an example for anionic ligand. Chloride is the ligand here. So you can see the final complex is anionic complex. Now the chelates. What do we mean by the chelates? So first we came to know about now number of terms today, right? The ligand, the coordination number, then the coordination dative bond, then the coordination bonds, right, like that. And the other term that you have to remember or to know about, chelates, right? What is a chelate? Actually, chelates are a class of coordination, cyclic coordination. Should be sure, cyclic word should be here. Should be they are a class of cyclic coordination compounds, right? For example, what you get from this one, the glycine and the copper 2+, they are cyclic, right? Let me draw it again here. Copper here, like this. Here nitrogen, here oxygen, here nitrogen, or cis trans also you can think of. Now this bond here, and this one here, and this one here, and this one there. And if you think about, let me take a different color, and this one, it is cyclic, right? It is cyclic, and again this one is cyclic, right? So the chelates are the cyclic. Chelates are the cyclic complexes, so cyclic coordination compound. So it is very important that you understand they are cyclic, right? They are close here. Copper, oxygen, again carbon, nitrogen. It's like a ring here. It is closed, so it is cyclic. Then we want to now let's move to the next slide. Okay, cyclic complexes are how we get the cyclic complexes now, the chelates. Cyclic complexes are formed, right? Cyclic complexes are formed when a cation, right? When a cation is bonded by 2 or more electron donor groups containing a single molecule. Okay, contained in a single molecule. So what it says, now you have the metal ion. How you get the cyclic complexes or chelates? When the metal ion bonded by two or more electron donor groups contained in the same ligand, right? It's we showed it earlier like that. The same ligand, but it contains two electron donor groups here. This one and this one. The in that glycine one, it is N atom, and the oxygen, the carboxylic acid. So there are two electron donor groups there. So definitely you are going to get a cyclic complex, which we call a chelate, which is an example for a chelate, right? So the chelate mean they are close compounds, the rings like thing. They can be 5-membered, 6-membered heterocyclic rings. Okay, you know, this is for example, for a ring you have studied organic chemistry. I know that. Something like that, cyclohexane, right? This is a cyclic one. This is a cyclic, right? This is a cyclic. Now, why we call the heterocyclic here? Now here completely different. Here the metal ion is there, and in the ring, this one, and this is oxygen, this is carbon, this is carbon, this is nitrogen. So not homocyclic, it is heterocyclic. But if you think about the benzene like thing or cyclohexane, this you can consider as a homocyclic. Why all the atoms here in the ring are the same. Oh, carbon, carbon, carbon. Homocyclic, same, right? And here they are not same, different atom at each of these points in the ring, and that's why we call them heterocyclic rings, right? So the important thing is important thing that you want to know, right? We just move to the next slide. Let me erase one. To the next slide. Hello. Oh, hey, come. Right. Right. Let's now move to the next slide. Now we came to know about ligands, right? Ligands are sort of neutral species or ionic species which can donate pair of electrons to metal ions and make coordination bonds, right? That is the definition of a ligand, right? For example, we have taken water, ammonia, chloride like things. Now the single and multi-dentate ligand, right? Now you just think about the word, the multi-dentate. The multi-dentate. What do you mean by the dentate? It's like when you say the dentate, it is something to do with your what is called the teeth, right? The dentate, right? It's like you have your teeth and you just having something between teeth, right? Like you have a ligand, and ligand is now sort of grabbing Okay, the metal ion. That is why it's called the dentate. So the single dentate and multidentate ligand. Ligands with single donor group. Ligands with single donor groups are called multidentate ligands. They are called multidentate ligand. Then the multidentate ligand, that means they have only one electron donor groups. Yes, water, if you consider water, yes, only one electron donor group. In ammonia, yes, only one electron donor group. And the ligand with two donor groups, two electron donor groups, we call them bidentate ligands. We call them bidentate ligands. Right. Example, what we have considered in the previous slide, the glycine. Right. This is an amino acid, simplest amino acids. And here, this one here, depending on the pH, in fact, this can undergo ionization or deprotonation. And definitely this here, the nitrogen and this one. And there are two. You can say there are two electron donor group. One is this one, other is the group. If we consider the group, this is the carboxylic group, and of the carboxylic group, this group is deprotonated, you get them oxygen -1, and in fact now there are this group, and this group. They are electron donor group now. Single molecule with two donor electron groups. It is an example for bidentate ligand. And here, look at here, trimethylene-diamine. Here you have this carbon skeleton here. And at the two ends of that, you have NH2 groups, right? And definitely now you know there are two electron donor groups in the same molecule, right? That this is the metal ion, the bond formation with the metal ion is indicated by arrows here. Anyway, what you should understand here, this is an example. This particular one is an again example for a bidentate ligand. Right, so this one here also example for bidentate ligand. Right, in this side, this group acts as one electron donor group, and this group from this side act as another the second electron donor group. Then the ligands with ligands with three electron donor groups. We just call three donor groups, right? So they are called tri. If there are three groups, we call them tridentate ligands. And the example here, this is you can see terpene here, terpene. Look at here, this nitrogen here, this nitrogen here, this nitrogen here. They all contain what we need, that is the lone pair electron pair. So that means, so this is one donor group, again another donor group, and three donor groups there, right? So so this is an example. Again here, this one, and this. Three electron donor groups there. So they are example for tridentate ligands. Then the next one, the ligands with four donor groups. The four donor group, ligands with four electron donor group. They are termed as tetradentate ligands. Tetradentate ligand. So the tetradentate ligand, here there should be four. Yes, this is one. It can make a bond with the metal ion. This is another one which also can make a bond, and this here another one, and this altogether there are 4 electron donor groups. They are each can make a coordination bond with the metal ion, right? With the metal ion. So we can now so two more example for tetradentate ligands here, right? So here one donor site, the other donor site, right? This donor sites, okay, all together 4 donor sites. So they right a similar yes, this and this one, right? So the example now for tetradentate ligands. So we can move to the next one, next slide. Again under multidentate ligands. Now it is with 4. It is with 4. It is with 4 or 5 donor groups in a single molecule. So this is our single molecule, the ligand. Let's see how many donor groups there. This is the donor electron donor group because oxygen has some lone pair electrons, and here nitrogen, and the other one, and 3, and the 5th electron donor site here, right? And similarly, if you look at this one, this example, see again this one, and again 3, this nitrogen, right? So those are the example for pentadentate ligands. Then the ligands with 6 donor group, which we call hexadentate ligands. Sorry, this is this. Okay, just forget about that. Those are the example for previous one, and this is the one for hexadentate. Example for a hexadentate ligand, right? So this particular one actually ethylene diamine tetraacetate. It called, why it is OH the deprotonated here. So it is the abbreviation is EDTA. So it is a very long molecule here, right? From here one electron donor group here, other electron donor group here, and here 4 electron donor group, and here in the chain, and here these 2 nitrogen are the 5th and 6th donor sites. So there are 1, 2, 3, 4, 5, 6 electron donor sites. Okay, and finally, when it makes a complex, it looks like this one. Now the metal in the center, and it is surrounded by this particular molecule like this, right? So it's like something, okay, something like you have something like this, right? These are in a one plane, and other 2 groups of the same ligand, one from the top and the other from that side. Usually it's like something like this, right? So we go to the next slide. Now the multidentate ligand versus unidentate ligand. Why we are so much worried about the number of donor groups in a ligand? Right now you can understand here. right, you can understand why it is multidentate ligands versus unidentate ligands. Multidentate ligands versus unidentate ligands. Right here, this particular the curve, the plot here you can see. This is these are the plots for the reaction of a metal ion with three different ligands, right? So the multidentate, what are the advantages? Multidentate ligands have two advantages. Multidentate ligands have two advantages over unidentate ligand, right? Multidentate ligands have two advantages over unidentate ligand. Now you understand multidentate ligands are much more favorable than unidentate ligand. Why? The reason why they have and what are the advantages? They generally react more completely. They react more completely and provide sharper endpoint. Now look at here. The multidentate ligand react more completely. Look at now the A is for A. The metal ion react with the ligand 1-to-1. That means the ligand, your metal ion, but the metal ion we consider it has a 4 coordination bond. In first curve, in first curve here, right? In first curve here, what we have provided the ligand here, ligand has 4. It is a tetradentate ligand. So it is a tetradentate ligand. All the binding sites just occupied in a one-step reaction, right? That's why it is called one ligand, one metal ion. For that sort of reaction, see the rapid changing region. It is very wide, right? It is very wide. It is very wide, right? Now go to the next, the same metal ion, but now react with your bidentate ligand. Bidentate ligand. If it is a bidentate ligand, two ligands should react with one metal atom or ion, right? This is what you get. In fact, it's a two-step reaction. First, one ligand come and make bonds, then the second ligand come and complete the other two coordination number. Okay, for that sort of reaction, what you know, it is 2:1. For one metal ion, you need two ligands, right? For that one, if you look at here, let me take different color. For that one here, the rapid changing region is like this. It is not that wide when you compare it with the tetradentate ligand case, right? So if you now see the third one, the same metal ion, now the unidentate ligand. One metal ion, 4 ligand molecules. 4 ligand species, whatever the number. Then now you just think for that one. In fact, this is, look at that curve. It's very hard to find rapid changing region, right? So that's why say we have some advantage when we use multidentate ligand over unidentate ligand. So okay, two are more completely reaction is more complete, and you get sharper endpoints. And ordinarily they react with metal ion in a single step. Yes, we know that now. and each of the curves involve the reaction of overall. So whether if it is the same metal ion, okay, usually for the overall reaction to complete all four bonds around the metal ion, for overall reaction, the equilibrium constant should somewhere around 10 to the power 20, right? So here 2 step, 12 and 18. Here 3 step, 8, 6, 4 and 2. Right? It happens in 4 steps, right? So that means a much sharper endpoint is obtained for single step reaction. For single step reaction, right, it goes from here to here. You get what we call for a case where we have single step reaction, and look at it always gives a sharp endpoint. You use really you need an indicator, right? So our choice now, so that thing will indicate multi-dentate ligands. So the multi-dentate ligands are our choice. Choice for what? For the titration of metal ion, or to use in complexometric titration, right? So you always think about if you have multidentate ligand and unidentate ligand, when you do the titration with the multidentate ligand, there are number of advantages. So you just think about that. It is very important you understand the thing, right? So we have completed this slide. We can move to the next one now. Right. Now now what we so far went through is some basic coordination chemistry, right? Called simple or basics in coordination chemistry, or sort of introduction to coordination chemistry, right? Where we came to know about what we mean by a complex in coordination compound, or how we get a coordination compound in reaction of metal ion with ligands, and what is a ligand, and what is a chelate, right? And electron donor groups and cyclic complexes, like that. Okay. Now we sort of have some knowledge about the basic coordination chemistry that is required for complexometric titration. So we can now think about the titration or complexometric titration. So here the titrations with, what is our ligand now? Titration with amino carboxylic acids. So what we use in fact for metal ion determination are the amino carboxylic acids. They are the complex formation reagents for metal ions. So particularly tertiary amines, right? Tertiary amine, you know what I mean by tertiary amine. Tertiary amine here, right? Tertiary amine mean no any hydrogen or not nitrogen, right? All these are groups here. So we don't know what are the groups here, but no any hydrogen there. All three bonds, some the groups are there, no hydrogen in them. Right. So for example, if you consider this particular molecule here, this particular molecule, now you just see the nitrogen here, this bond, this bond, this one, it is tertiary, right? It is the tertiary amines. Tertiary amines that also contain carboxylic acid groups form remarkably stable chelates. Very, very important thing that you should understand. So for complexometric titration, we always use amino carboxylic acids. Usually they are tertiary amines containing carboxylic acid groups, right? When the ligand contain amino group and carboxylic acid groups, the complexes which are chelates here are remarkably stable, right? They are remarkably stable. So that is the important thing here behind using amino carboxylic acid as the complex formation reagent in the titration of metal ion, right? So our real reagent is ethylene diamine tetra acetic acid, right? This is also you know this is the E, D, and tetra acetic acid, EDTA. It is called EDTA. This is the structure. Ethylene diamine, right? This is the ethylene, the backbone of the ethylene diamine, and to that there are 4 acid. T is missing here. Okay, should be acetic, tetraacetic. Well, where are the tetraacetic? Here, acetic group 1, 2, 3, 4. Tetraacetic acid. Ethylene diamine tetraacetic acid, EDTA, right? How again it's sort of the way you can think about its structure, right? It's not a flat molecule, in fact, right? And important point here is that you can note it very clearly. This is a multidentate ligand. And very importantly, it is a hexadentate ligand. That means EDTA has 6 electron donor groups to make coordination bonds with metal ion or neutral metal. So what are these? This is the one of the all these 4 carboxylic groups are electron donor groups, right? Where are the other 2? This one and this one, right? You now have 2 from nitrogen and 4 from carboxylic acid group. Sorry about that. It should be COO minus, right? So you just think about this particular one here, right? This particular one, the structure when it make a complex with a metal ion, you can see the metal ion in the center there. Metal ion in the center here, you can see the metal ion, and two nitrogen atoms in the ethylene diamine group, right? This is ethylene diamine group here, and one acetic acid group here, and the other acetic acid group here, and this acidic acid group here, and the fourth acidic acid group here, right? That's the way you just imagine how it looks like. Finally, you have the metal line here, right? One from this way, the other one from this way, the other from this way, and the like this, right? Here nitrogen, and here O, here O, and the other two, for one from this side, right, and the other from this side, right? So that's how you can just imagine the shape of the complex. Now this is a chelate, right? This is an example for a chelate. This is a cyclic complex. The cyclic complex. You just think about that one. So we can move to the next slide. Dissociation constant for the acidic groups. Right? Acidic groups here. So let's see acidic groups. There dissociation constant of acidic group. So what are the acidic group? This one carboxylic group or acidic group, or carboxylic group here, right? So you have the same here. Just forget about this. 4 carboxylic group. This one, right? 4 carboxylic groups here, and they are dissociation constant K1, K2, K3, and K4. And 4 groups. By looking at their values, they all are minus 10 to the power 2, 10 to the power minus 3, minus 7, minus 11. So these carboxylic groups are in fact behave like weak acidic groups, right? They are not strong acidic groups. They are weak acidic groups. Now let's which is the K1, which is the K2, which is K1, which is K2. Now this is the way you assign this K1 to K4 to 4 acidic groups here. Look at here, K1 and K2 are in the same order of magnitude, K1 and K2. Look at minus 2, minus 3. But these are different from these because minus 7, minus 11. These two are sort of in the same order. So what you have to think about, if you want to get all 4 carboxylic acid groups to dissociate, the first one is easier compared to the second one. Again, the second one is easier compared to the third one. The third one is difficult, and the fourth one is the most difficult. The reason, by dissociating the carboxylic group, you get some charges on the molecule, minus charges. The minus charges on the molecule really affect the dissociation of the next carboxylic acid group, right? So what we first select, the first 2, K1 and K2, are assigned to the carboxylic acid group located in the opposites. If you say, okay, this is K1, this is K1, and this you have to select as the K2, right? Because they are the one located at the opposite ends of the long molecule, right? Then you have to think about 3 and 4. Then the dissociation constant of 3 and 4. Now the look at here. Now this is gone, right? This hydrogen gone. You have minus charge there, and this is gone. You have minus charge there. Here you have minus charge on this oxygen there. Right now, in the molecule, in fact, there are 2 charges, but they are opposite in the same line, but they can really affect the ionization of this one, and also they can affect the ionization of this one. That's why 3 and 4, these two are for 3 and 4. So if you label this as 3 K3, definitely the other one is right K4. Right, that is how you do it. They are weak acid groups. So what you just want to write like this you get I don't want to draw the entire molecule here. Here you get minus charge here, and oxygen, carbon, and the other part of the molecule, right? So that is the thing that you need to think about. All these 4 undergo very identical deprotonation or dissociation there, right? The other one, the dissociation, the dissociation is difficult, right? 7 are very difficult. This right. Okay, move to the next slide. Here, EDTA species. What are the EDTA species? Or we indicate them using some abbreviations. What are the abbreviations we use? This for example, I just take without hydrogen, the rest of the molecule we designate it as Y, is Y, right? If it is Y, this particular one you can say H4Y, right? H4Y. Now if you lose one here, one proton here, then you can say it is H3Y minus. If you lose another proton here, the dissociation there, then we can say it is H2Y2 minus. Okay, now if you lose 3 here, it is H this one. If all 4 carboxylic group undergo dissociation, what you get here? Y4 minus. Y4 minus, right? Now you have to think in a this way also, right? The pH, right? You can get this species change in pH, right? Either Y, this is Y4, either Y4 or Y4, H4Y, H3Y minus, or this one, or this one, or this one, in your solution you have all these species. Not only all these species, there are two more species you are thinking about. What are these? The which way the pH changes, and also depending on your nitrogen here, right? In acidic side, what happened? Your nitrogen here, it become protonated like that, and this one also, and both nitrogen, same thing can happen to both nitrogen, and they have two different Ka values there, right? So so using that, thinking of that, so what you can say now, now you have in this situation, what is this situation? If you have hydrogen plus charge there on nitrogen, there's a proton there. What you can see, what's this species now? H6 2 plus, H6 2 plus, right? If only one nitrogen is protonated, then you can see plus. So altogether, you can see 1, 2, 3, 4, 5, 6, 7 species, right? Doesn't matter from which species you start, whether you start from this species, or whether you start from this species, or whether you start from this species. Once you start in the whatever the species you are, it is in the solution. So depending on the pH of the solution, so you are going to get all these species in a solution, right? Right, if you put 100, now it is distributed among 7 species, right? The composition, we call that what is the composition of these the various EDTA species, often abbreviated this one, and their composition in a mixture or solution depends on the pH, right? Depend on the pH. So we can just go through how their composition changes. Go to the next slide. Now this is right, acid base forms there, right? So we look at here. Let me take the color pen again, right? So this curve here, right? That curve for this species, and this curve here, one curve coming from this side here, like that, it is for this species, and another curve coming from this side like this, it is this one, right? And this one like that. There are like 7 curves like that, right? This way you can see the pH, how the pH changes, right? How the pH changes. So starting from the if you change the pH from very low value to high value up to 12, 13 like that, then the fraction of each of these species, okay, the composition, what happened actually when this is in its maximum, right? This is H6, this one is in its maximum close to this pH here, right? And the H5Y plus is in its maximum when the pH is somewhere in 1, right? Or nitrogen is protonated. Here both the nitrogen protonated maximum, and their composition changes like this. Once the composition changes, other species appear, right? The other species here like that. This the other species here H2Y2 minus, and its maximum is somewhere here, right? And at that particular pH, it is very close to 1. For this one, at this particular pH, this is close to something 1 there, right? It is something 1, close to 1, about 9.5, right? Now you just want to understand one thing. For the metal line here. Now there are 4 carboxylic groups there, right? Drawn with oxygen and 2 nitrogen, and this is the protonated one, the deprotonated carboxylic acid groups. Now 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6 electron donor groups of the EDTA molecule. The metal ion is in the center, and they should be, to make bonds here, the lone pair should be available, right? Lone pair should be available, as well as all 4 carboxylic groups should have been ionized or dissociated, right? That means what you need in the molecule, what you need in the molecule, 2 of these not protonated, and all 4 acid groups are carboxylic groups are protonated. That is the deprotonated. That is the situation we need in the EDTA molecule to make 6 bonds. So that means what you need, in fact, to make the coordination bonds in the metal ion, to make the complex between EDTA and the metal ion. This is the species we should need, this one. So you have to just think about that. To get the maximum of those, somewhere here 12, you get the 100% of this one, no other species. But this species begins to appear somewhere above pH 8, right? Just above pH 8. Y4 minus just begins to appear, right? And that means for your EDTA titration, now you have to think about that. You need to think about what is the pH you want to maintain, right? It's very important. For the reaction to happen, there's a particular pH that you have to maintain. That also depends on the metal type of metal ion. Just think about that. It's very important. You understand that the one I just let me finish the next slide, probably the last one. Go to the last slide, okay? The last slide. Variation of composition of EDTA species is pH. We noted that, and also we said that what we need is Y4 minus. The important species that we need for the reaction to happen there during the titration is Y4 minus. Therefore, we have to maintain the pH. Whatever the species we need, so we have to maintain the pH accordingly. So the Y4 minus, what is alpha actually? The sort of the ratio. Or it's give the degree of degree or the fraction of alpha indicate fraction of that particular species, fraction of that particular EDTA species. What is the EDTA species? Now we consider Y4 minus. The fraction of Y4 minus species in the solution is equal to Y4 minus concentration, and this concentration, this concentration, this concentration, this concentration, this, right? And definitely what I said, this is equal to the total concentration of EDTA. That is the total concentration of EDTA, right? This plus, this plus, this plus, this plus, this plus, this plus, this 1, 2, 3, 4, 6, 7. 7 species, concentration of 7 species together, we call the total concentration, the total concentration. So we can write down the equation again, right? The fraction of Y4 minus species is equal to concentration of Y4 minus and concentration of all the species together here. Summation of all the concentration of all the species. What are all the species? All these 7 species. Some of these species may be very negligible, right? First 2 species may be negligible. So it is very important that you consider the 2 nitrogen groups should be free and carboxylic group should be deprotonated for all the 6 binding sites to react with the metal ion, right? And if you want to calculate alpha 4, this is the equation you can calculate, right? For this one, you definitely need K1, K2, K3, K4, K5, K6. Now there are K5 and K6. K5 and K6 for the ammonium group. There are 2 ammonium groups, yeah, right? And this are here. There are if you know K1, K2, K3, K4, K5, K6, and if you know the pH, you can definitely calculate alpha 4, the fraction of alpha 4. Now look at here, the pH value increase from 0 to 14, really basic condition here, very basic condition here at this end. And when the pH is very close to 0, you look at here, the concentration of whatever the alpha 4 is almost, I mean, negligible, right? These all are very negligible, and they begin to it begin to increase. It begin to increase here, increase, but really somewhere here you can see some real increment. And when it comes to this one here, 0.3, 0.81, 0.98, and it become 1. Look at here. At 13, it become 1. Right? So for most of the metal, so you have to use, you have to do the titration under controlled pH. Right, so it should be something around 8, I think, or 9, right? To make sure you have sort of alpha 4 minus. As the reaction happen, now you get the alpha 4 produced there continuously, but you know the pH is a factor there, right? So then we have this, I think. Come to that is the last slide, I think. Yeah, that is the last slide. So I'm going. So I just want to know. I gave the demonstrator to upload the practice test with the answers. Did you see it in the LMS? Have you seen it in the LMS?
Yes.
It is there. Answers are also there, right? So the right. So now I have already uploaded whatever the slides of lessons I have done online, except today one. But I have to complete the today lesson. It might take another 3 hours to complete. So once I finish that one, I will upload this EDTA or complex symmetric titration PowerPoint presentation to LMS. Okay. So the what else you want to know now? If you want to know something now, okay, we have used like we have few minutes. Okay, I have scheduled this for 1.5 hours. There are only 119 students today. Today the number is very low. It is 130 students today. At the beginning, somewhere it was the maximum was 131, and it is now it dropped to 120 something during the lecture, toward the end of the lecture. Now that's the situation. What else you think you want to know now, or before I stop, because we have a few more minutes, okay, left. If you have any question, I just